Begin. There we go. Okay. So, good morning, everyone. Hope you are all doing well. Hope this week is going all right for you guys and all of its unique ins and outs. We are going to continue talking about Chapter 5 and 6 this week, today. As a reminder, the Chapter 5-6 combined homework, quiz, and lab are presently due next Tuesday at midnight. So we'll meet during the day, and then you can turn them in at any point before midnight, which means that you don't have to worry about getting the lab done today. If today is your lab, it is due next Tuesday. You have time to work on it. I sent out the video lectures for everyone to watch so that you could get the information and then we can discuss it here together. So I'm going to begin today with what questions do you guys have about the material? We went over most of at least some of Chapter 5 directly in the lecture last time. We can just pick right up where we left off, but if there's any, I want to go ahead and ask if you guys have any specific questions or things that you'd like to talk about right now. Okay. Well, in that case, let's just keep moving forwards in the material. So, I recommend you have the slideshow up as we are going through it together. I will tell you what slide to be looking at and show you what slide to be looking at any given time. So, just to start that, I'm going to screen share really quickly. Nope, that's the lab. Okay, so this is the Chapter 5 notes, and I feel a sneeze coming on, pardon me. Terribly sorry about that, everyone.
Bless you.
Thank you. It's allergy season part 2, and I hate it. So
yeah, I get that in the spring.
Has anyone found out why pollen allergies are suddenly acting up? I don't normally get this in fall. I get pressure allergies in winter, but not fall.
There's a lot of I don't know. There's a lot of flowers and like winter grasses that start growing in like fall.
I feel like that doesn't usually happen to me.
I don't know. I just know it's bad this year. It's bad here in Knoxville too.
Okay. Wait. Okay. But on the slideshow, I'm currently showing you slide 6. This is where we left off. We did this example. Wait, did we do this example before?
I don't think we did this example.
I'm getting my lectures mixed up. Okay. So we actually left off here, I think, looking at these formulas, density and pressure. There's 2 quick sample problems here. First one is about density. So this is actually slide 4. Slide 4, quick density sample question. In this particular question, you are told the volume of a boulder and the density of a boulder and asked what the mass of such a boulder would be.
How do we say like the volume? Because it's like 5 and then there's the caret and the meters caret 3. How do we say that exactly?
So I have wrote it on the board as I would prefer to write it if PowerPoint would let me. 5 meters cubed. It is meters raised to the 3rd power because volume is a 3-dimensional measurement of space. You measure the x-axis, the y-axis, and the z-axis. So 1 meter cubed is an object like a cube that is 1 meter by 1 meter by 1 meter because it's three axes, it is meters cubed. And density is defined as mass over volume. So this is the density of granite. This tells you how much mass is in the volume of granite. The units here are kilograms per meter cubed because it's the mass contained within the volume. So in this particular example, we know the boulder's volume and its density. We are asked to find its mass. This is a method that a lot of scientists will employ in order to figure out what something is. Metallurgists will take something, figure out its volume, figure out its mass, use its density to identify what it is. Sometimes if you know density and volume, you can find mass that way, vice versa. So we're going to use our density formula, which I didn't write on the board. I'm sorry. Density, which is a lowercase rho, is equal to mass over volume. So 2,691 will equal our mass over 5 meters cubed. Keep in mind, this is big capital V for volume. This is different to lowercase v for velocity. So multiply both sides by 5, and you will have a very large amount of mass for this boulder because, scientifically speaking, boulders are heavy. And my calculator always ends up at the bottom of my bag. So the answer is 13,455 kilograms, which is again a lot. Density is just a combination of the statement of a object's mass and volume. If you have one, you can use density to find the other. Density is going to become important because in a second, we're going to transition into talking about floating, whether or not objects will float and the forces involved in floating. And density is very involved in floating because you've probably heard the statement that if you want to float something in water, it needs to be less dense than the water. Density matters to both the object that is floating and also to the fluid it is floating in. Speaking of that, we're going to move on. The next slide, this is slide number 5, has a new formula on it. This is an additional formula for pressure. Last time we talked about pressure equals force over area. Here, this is a new formula. Pressure equals density times gravity times height. This formula has a very specific use. And where's my blue marker? There it is. So, pressure is defined as force over a surface area. That is what the pressure is literally defined as. But if an object is submerged in a fluid, so there's a big caveat here. This formula is for an object submerged in a fluid. You can use this formula to figure out the pressure that the fluid is exerting upon that object. As an example, let's say you go swimming in a pool. So this is a very poorly drawn side view of a pool, and you are in the water a certain depth below the surface. That depth is represented by h because there is a certain height of water above you. If we consider your position to be 0, there's a certain height of fluid above your head. And when you are in water like this, the water is all around you, and this height of water above you is pressing down on both you and the water at the same depth as you. That force, that downward force, is going to be exerted on you and on the water around you, and that is what causes the force that the water is going to exert on every inch of your surface area. Now, fluids will always press into an object perpendicular to its surface area. So even though the weight of the water pushes down, the water to the sides of you are going to push in, and the water beneath you is going to push up. It's because the water, it's just compressing you. It's trying to push you out of the way on all sides of you at the same time. So it just ends up pushing into you. The water on the sides of you, like when you get in the water, you sort of push the water out of the way with your body. Like the space you're in used to be occupied by water. So the water pushes against you on all sides, trying to get back into that space. And because your body is there, you won't let it. You exert a force outward on the water will exert a force inward on you. Now, how much force the water can exert depends on the water's density. The more dense the fluid is, the more force it can exert, because the more dense something is, the more mass there is per unit volume pressing into you. This is why it is easier to float in more dense fluids. As an example, water is a fluid, liquids count as fluids, and typically humans have shown to be able to float in water. If you lay on your back and are very still, you can float at or just below the water's surface. Now remember that air is also a fluid. Gases and liquids both count as types of fluids. So you are presently submerged in a fluid. There's air all around you exerting air pressure on your body. Air is not very dense. Humans are much more dense than air, which is why we don't float in air. We float in water, which our density is about equal to. We don't float in air, which we are much more dense than. So, this formula, the formula here, pressure equals density times gravity times height. This formula is to be used when you are submerged in a fluid. The H term represents the height of fluid above you, your depth in the fluid, and the density term represents the density of the fluid, because this is the pressure that the fluid exerts on you. The fluid is what is exerting this pressure, so you need the density of the fluid here. So in this particular example, if we were looking at being a certain depth in water, you would need the density of water. And that would tell you the pressure that the water exerts on your body. If you have any questions, please speak up. I will check the chat as well.
On the quiz, it's a question about like 3 cans or like a bottle. So it's one that's pushed in, that's like squeezed in. So would that be the water surface? Would that be a water surface? I'm
sorry, CJ. There's a lot of sound, and it sounds like you're not very close to the microphone. I'm having a hard time hearing you.
My bad. I'm not at home right now. So it's a question on the quiz. It's like three figures of a bottle, and it's like 3 of them that says like water surface, in the plane, and something else. So with the one that say water surface, would that be the one with the bottle squeezed in?
I don't.
I'm sorry, can you hear me better now?
I can hear you better now. You were asking about a specific homework question?
Yes, sir.
Now, I don't remember every homework question off the very top of my head, so I need to check that.
Like I said, I'm not home right now, so I'm just trying to get a clear understanding of it. I can't really share it right now.
Okay, no, I understand. Everyone else, go ahead and turn your attention to the next slide because it's going to have a sample question we're going to use. Is this question 5, the 3 cans of grape juice?
Yes, sir. And then it has like three sections where it say like water surface, airplane, and something else.
Okay, so that question has to do with the atmospheric pressure at different heights. So that it does relate to this new formula. Right now, you are surrounded by air at sea level. So if we were looking at this formula to talk about the air pressure on your body, we would plug in the density of the air, 9.8, and the height of air above your head, which is the height of the atmosphere. Now, the human body and also our soda cans were invented to exist at sea level. Sea level is, I presume, the height everyone is at right now. It is flat ground. You're not on a mountain. You're at the level of the ocean at Earth's surface. So you plug in a specific height to find the standard atmospheric air pressure at that level. And at that is the level that soda cans are built at and designed to be used at. So they look normal at sea level. Meanwhile, if you go further down into the earth, there's then, if you were to increase your depth and go further down in this pool, that means that there's going to be more fluid above you. That means there's more above you pressing down and pressure will rise. If pressure rises, there's more force pressing into the object. So the further down you go, the more the pressure presses inwards. If you increase elevation, though, there's less fluid above you. It doesn't exert as much pressure, and that means its force gets weaker and things tend to bow outwards.
Okay, so yeah, all right. I understand that one better now.
Okay. Now, slide 6, we're going to do a sample problem about this. We're going to show what I just said using math. We have, as a sample question, this is slide number 6, a person in a pool. We are 3 meters below the water's surface, and the density of the water is 1,000 kilograms per meter cubed. This is a handy number to know off the top of your head. The grams and kilograms and meters were sort of defined based on water, which is why the density of water is a nice even 1,000. If we were looking at kilograms per liter, it would be 1 kilogram per liter. The definition of liters, all of these units were based on quantities of water. So density of water, 1,000 kilograms meters cubed. And we are asked, what is the pressure at this depth? What is the pressure from the water on you at this particular depth? So we turn to our new pressure formula. This is the formula for the pressure when you are submerged in a fluid. Density times 9.8 times h. So we have the density of the fluid exerting the pressure times 9.8 times your depth. So it's going to be 1,000 times 9.8 times 3. And that is 29,400 pascals. The unit for pressure is pascals. And this would be the additional pressure added onto you by the water. Now, we don't usually talk about pascals in common English parlance, at least not in the United States. So a lot of people don't have a very good sense of scale for what this number would represent. So to give you some scale, you are currently under a standard atmosphere's worth of air pressure, the pressure on you just from Earth's atmosphere above you. That pressure that you are experiencing right now is equal to 101,325 pascals. This is the pressure you're under right now. This is the pressure you're always under at sea level on planet Earth. This pressure that we just calculated, the 29,400, this would be added to this pressure when you go into the water, because before you enter the water, you're already at this pressure. After you enter the water, there's still this much air above you, but now there's also this much water above you. So this is the pressure created by the water. This is the pressure created by the air above the water. So this is what you start at before you jump in the pool. This is what is added after you're in the pool. This is just from the water itself. And this isn't a huge amount to add to the pressure you're already under. It's less than a third, maybe about a fourth of the pressure that you're already under. So you could detect it. You would feel, yes, there's slightly more pressure on me. I am in the water. I can feel this, but it wouldn't be enough to injure you or cause any sort of issues. This is only about 10. This is like a 10-foot deep pool. So this added to this would be what you're really experiencing. And your body is designed to tank this air pressure. You are built to live under these air pressures. You don't notice it because our body is designed for it. So increasing it just by this much is not a huge deal. But to give an additional sense of scale, there is an extra question on this particular slide. If your eardrum has a surface area of 7.85 times 10 to the negative fifth meters cubed. This is the actual surface area of most people's eardrums. It's a very, very tiny patch of skin that literally beats like a drum when sound waves hit it. If this is the surface area of your eardrum and this is the pressure that the water adds to you, how much force is the water exerting on your eardrum? So if we know pressure, we know area, and we want force, we turn to the definition of pressure. Pressure equals force over area. So 29,400 is equal to force over 7.85 times 10 to the negative fifth. And you're going to want to multiply both sides by 7.85 times 10 to the negative fifth. And you should get a force of about 2.31 newtons. Now that's not a huge amount of force. But you would feel that force directly on your eardrum, which is why occasionally going deeper into water makes your ears hurt. Especially if you go even deeper than that. Now again, this is just the pressure added by the water. You're already under more pressure than this just from the atmosphere. So this is just the force added to your eardrum in addition to the force the air is already exerting on your eardrum. Your eardrum is currently under more force than this just from the atmosphere. This is just what's added to it going this deep into the water. So your eardrums are actually pretty tough. They're designed to take more force than that already, and they can handle that much more force when you go into the water. So that is the first three formulas, actually, that we talked about so far. Any questions before we switch gears and start talking about buoyancy? Okay. Excuse me. Okay. I'm going to clear off the work from this sample question so that we can talk about our next formula and our next concept. So please move on to slide number 7 on your notes. And these slides, slides 7 and 8, do have animation that that is intentionally added to show exactly how the forces on a floating object add up. So for slides 7 and 8, I do recommend you go into regular slideshow presentation mode to see the arrows as you click and as they appear. So we're going to talk about why things float. Now, floating is caused by buoyancy. Now, and I'm going to spell that. So buoyancy, which is pronounced which is spelled B-U-O-Y-A-N-C-Y. The principle of buoyancy. Buoyancy is the force that creates floating. And this force comes from the pressure that the fluid you are floating in is exerting on you. So I want you to look very carefully at slide 7. We have on this particular slide a cube that is floating in some fluid. It is floating in water. Now, but when you just boot the slide up, and I'm actually going to, I'll screen share this so that you can see as I see. So I'm in presentation mode. This is what you'd be seeing if I pulled this up in class. We have a cube that is floating in water. And when any object enters the water, your volume pushes water out of the way. Water wants to be where you are, and you are forcing it not to be. That's why you exert pressure out on the water to push it out of the way, and that's why water exerts pressure back inwards on you. It's Newton's third law. Now, click once, the water appears. Click twice, and these arrows on all sides. On the left side of the object, the pressure is going to press inwards to the right. But notice how the arrows are changing size. They're increasing as you go down. That's because if we look at the formula we just talked about, pressure equals density times gravity times h, the deeper you go, the more the pressure is. So the bottom of the object is under more pressure than the top of the object because it is deeper down. That's why the pressure arrows got bigger towards the bottom of the object. If you press forwards again, you'll see the same arrows on the right side. Notice, again, as you go deeper, the arrows will get bigger. But the left and right sides, the forces on those sides are ultimately going to cancel out, because at the very top, there's two weak forces pressing inwards in opposite directions. At the bottom, there's two bigger forces pressing inwards in opposite directions. So on all sides, on the left and right, those forces are ultimately going to cancel out. This is why when you are floating in still water, if you're just in the pool, lazily floating around, you will just sort of remain in place. There's no net force left or right if the water isn't itself moving. Press the arrow again, and we will see the pressure at the top of the object. Now, we're assuming this object is under the water, that it is submerged. And notice that these arrows, if we're assuming this is a cube, the top of the object would be horizontal. So the force from the liquid is going to point vertically downwards. Notice, though, that these arrows are all the same size, because the top of the object, if it's a flat cube, is all at the same depth. So these arrows are all the same size. Now press it again, and we'll see the buoyant force from the bottom. This is the pressure on the bottom of the cube. Those arrows all point upwards, and they are bigger than the ones at the top, because the bottom is deeper than the top is. Therefore, the pressure down there is greater. Which means, press the arrow one more time. Actually, if you get out of presentation mode, thank you very much. If you get onto presentation mode, we're on slide 8 now, actually. Press it one more time, and the side arrows cancel out, so we're just going to get rid of them. And since the bottom arrows are bigger than the top arrows, the net force from, like the net pressure from the water points upwards. This is the buoyant force. This is the force pressing up on the object to make it float. And this is because this comes from the fact that the pressure at the bottom is greater than the pressure at the top. So the net force that the water exerts is upwards. This is the force that makes things float. This is the buoyant force. In order for something to be stationary floating in water, if you throw something in the pool and it doesn't sink, if it just floats in place, it means that the buoyant force upwards is equal and opposite to the force of gravity downwards. If those forces add up to 0, the object will stay where it is and it won't accelerate by sinking. So we're now on slide 9. This buoyant force, this concept of floating, is called Archimedes' principle. I hope most of you have heard of Archimedes. I believe he was a Greek philosopher who rather famously, like the story behind how Archimedes discovered what would become this formula is Archimedes was in a bath, and he noticed that as things were added into the bath, they displaced water, and the water level of the tub rose. And you can use this to measure the volume of something that you add to the water, but also being in water creates the buoyant force that makes them float. And very famously, he then ran around town screaming, "Eureka, I figured it out." So this formula right here is called Archimedes' principle. And this tells us what the buoyant force on an object floating will be. So buoyant force, FB, this is a force, so it is measured in newtons. This is a force, it's just a specific kind of force. FB is equal to density times volume times gravity. Now, something important to note is, and this is on slide 9, the density is the density of the fluid. This is the density of the fluid creating the buoyant force. But the volume is the volume of the submerged object, because that is the volume of water that has been pushed out of the way. So the volume of the submerged object is the same as the volume of water that has been displaced. That volume of water is pressing into the object, trying to get back where it was. And based on the density of that fluid will affect how much force and how much pressure it exerts. So we have density of the fluid, I'll even add that up here. Density of the fluid, volume of the object times 9.8. And this tells you the buoyant force. Whenever you go swimming, when you enter the water, the water is always going to exert a buoyant force upwards upon you. This is why you will always feel lighter when you're swimming than when you're just walking around normally. It's the reason why we are able to swim at all. If there was no buoyant force, we would all sink like a rock. But because there's a buoyant force pushing us upwards in the water, we're light enough so that you can generate enough force by kicking your arms and legs to keep yourself at the surface of the water instead of sinking. The buoyant force is pushing upwards on you, and if you are an object, gravity pulls you down, and the buoyant force pushes you up. When you are floating, when you are perfectly level, the buoyant force upwards will equal out with the force of gravity downwards, and that's why you remain stationary. If these two things aren't equal, you'll sink. Well, okay, if gravity is bigger than buoyant force, you will sink. If buoyant force is bigger than gravity, you'll be pushed further out of the water. So this is the math of floating. This is where floating comes from. Any questions about any of this before we start using this formula? Okay. We're going to move on to an example where we can utilize this principle, and a real life place where buoyancy comes into effect is with submarines. The whole point of a submarine is to be able to use buoyant force to be at the depth you want to be at. Submarines can change what depth they are at, and they do that by changing basically their weight. The buoyant force on the submarine will press up on it, and then the submarine is able to take water in order to increase its weight, and when the weight is bigger than buoyant force, it will sink. So you're going to find the buoyant force on a submarine. This is the example on slide 10, and this particular submarine is floating on the surface. So this is our very quickly poorly drawn submarine, and I want to draw your attention to any time you've ever been to the beach or the pool and seen something floating. When things float, are they perfectly standing on the water's surface, or are they partially submerged?
They're partially submerged.
Partially submerged, very good. In order to create buoyant force, some amount of the substance has to be under the water, displacing a volume of water. So when a submarine is floating on the surface, the water level isn't down here. the bottom of the sub is not just dancing across the surface. The water level probably comes closer to right about here. You're high enough up so that the periscope can do its job, but most of the sub is still probably under the water. So we have a submarine. It is in seawater, and we are given the density of seawater. Notice that seawater is 1,025 kilograms per meter cubed. This is slightly more dense than fresh water because seawater has salt and other things in it that the same amount of water has more stuff in it if it's salt water because there's salt and other things dissolved in it. So seawater is more dense than fresh water because it literally has more stuff per unit volume in it. So that's why this density is slightly bigger than a second ago when we were using 1,000 for the density of pool water. So this is the density of salt water. This is the kind of water that this submarine is currently floating in. The first thing we are asked is, this submarine has a mass of 43,000, am I saying that right? 43,000 kilograms. It is very, very massive, which means it's also very, very heavy. So very frequently, we will build very heavy objects, submarines and boats, that are able to float, despite the fact that they are themselves made of metal and very, very heavy. You do this by specifically weaponizing the buoyant force, like we're going to do here. Now, the very first thing we are asked is, if the submarine is floating right here, what must the buoyant force acting on it be? Now, this first question doesn't actually use the formula we just learned, because this formula requires us to know what the buoyant force is and the object's volume. We don't know that yet. What we do know is, if the submarine is just stationary, floating at the surface, if floating, then the force of gravity must equal the buoyant force. So this is kind of a new formula that you can add into the corner of your notes. If something is floating, the buoyant force must be equal to the force of gravity. So all we really need to do right now is find the weight of the submarine. And since it is floating, buoyant force must be pressing upwards by the same amount. So Fg equals Fb. Fg is equal to mass times 9.8. So 43,000 times 9.8. The buoyant force on this submarine is going to be 421,400, which is a lot. That's a lot of force. So we found the buoyant force. This is the force literally keeping the submarine upright. Now I'm going to stop presenting so that you can all see the math on the board next. The next thing we are asked is, presently, while this is happening, we've already established that part of the submarine is going to be beneath the water, part of it is above the water. We are told the amount of submarine under the water, the amount of submarine above the water is 1/5 of the submarine's total volume. That means the amount of submarine under the water is 4/5 the total volume of the submarine. most of the volume is under the water. And because most of the volume is under the water, that's displacing a lot of water. It's pushing water out of the way in order to push the submarine upwards and create this buoyant force. What we're asked is, basically, what is the volume of the submarine? What is the volume of the submarine? So we now know the buoyant force. We know the buoyant force, and we know the density of seawater, and we know 9.8 is G. So we can now use this formula to find out the volume of the submerged object. So buoyant force equals fluid density times the volume of the object times G. So 421,400 is equal to density of salt water, 1,025, times volume submerged. This is volume submerged times 9.8. So the submerged portion of the submarine, we're going to divide both sides by 1,025. Then we're going to divide both sides by 9.8. The submerged portion of the sub has a volume of 41.95 meters cubed. That is how much volume of submarine is under the water. This is not the sub's total volume. This is the amount of it that is under the water, because only the amount beneath the water contributes to buoyant force. This 1/5, like the periscope, doesn't count because it's not currently displacing water. Only the amount under the water counts. Now, to find the total volume of the entire submarine, we know that this number here is equal to 4/5 of the total volume. So we can simply multiply both sides by 5/4 and find the submarine's total volume, including what's above the water, is 52.44 meters cubed. That's the total sub's volume, which isn't factored in at this depth, but the way that a submarine will sink is it will take water into its tanks. It has tanks that store water inside of them, and when it does that, the weight of the submarine is going to increase, and if the force of gravity is bigger than the buoyant force, you will then begin sinking. Eventually, the whole sub will be underwater, and then the whole sub's volume will factor in. But right now, as it's floating on the surface, only this much is contributing to the buoyant force. Any questions about this example? Okay. It is now officially 10:50. So if you have other classes you need to get to, if you need to start filtering out, that is absolutely okay. There's one more formula in this set of notes that we'll talk about tomorrow. We will also load up the Chapter 6 notes tomorrow. Chapter 6 isn't very long. It's just more pressure formulas. So tomorrow we're going to try to wrap up 5 and 6 together. I'll let you know more information about that tomorrow itself. But thank you all very much. If you have any questions at all, email me. And again, I have during what would be lab time, I'll be in here available to answer any questions you have. So do your notes, work on your assignments, watch the videos. It's just the same information again, but you can start, stop, rewind. and let me know if you need anything. I'll be here. Thank you all and have a great day.